11C, center of mass and angular momentum. 11.14 explosions and center of mass. A fireworks rocket streaks into the sky. The initial burst throws out sprays of light. It isn't your imagination if it seems like the whole pattern of color continues to climb with the same direction and speed as the original rocket. If you do not look carefully, the parts of the explosion just seem to scatter randomly. However, if it were possible to plot the positions of all the particles of the rocket during the burst, you would find that their average positions would correspond to the original trajectory of the rocket's center of mass. Center of mass is an important and useful concept in physics center of mass for studying the behavior of systems containing two or more objects. The center of mass is the point in space where the mass of the entire item is assumed to be located for the purpose of determining the momentum of the system. Though conceptually easy to understand, actually determining its location requires calculus for all but the simplest systems. In general, the center of mass is proportionately closer to the parts of a multi-body system that have the greatest mass. Thus, in the moments following the rocket's burst, the most massive parts of an exploding fireworks rocket will be closest to the point of explosion because they have the greatest inertia, and the least massive will be the farthest away. If you could run the explosion in reverse, it would seem that all of the particles converged in one great simultaneous, inelastic collision. This is a reasonable approximation of the situation if we ignore the mass of the explosive. If we consider the entire collection of particles resulting from an explosion to be the system, then the most significant forces acting on the particles during the instant of the explosion are internal forces, because internal explosive forces are usually very large compared to external forces such as gravity and air resistance. They will predominate when affecting the particle momenta. At the instant of the explosion, internal forces do not affect the total momentum of the system. Therefore, the sum of the momentae of all particles immediately after an explosion or disintegration is equal to the initial momentum of the object, assuming external forces are insignificant. P cis BFR equals sigma pi aft, where sigma pi is the vector sum of the momenta of all of the individual particles. Although momentum is conserved to a good approximation, the total kinetic energy of the particles is not. The forces that accelerate particles in explosions and other kinds of disintegrations come from chemical, mechanical, or other non-conservative sources. Angular momentum. A mass being whirled around on a string or a spinning wheel has momentum, but its momentum is somewhat different from the momentum of a mass traveling in a straight line. Mass moving in a circle is said to have angular momentum, L, which means momentum associated with circular motion. Let's look at a dimensionless article of mass m, orbiting a point at a distance, r, with tangential speed vt. The magnitude of the particle's instantaneous linear tangential momentum, P equals mvt. Angular momentum is the product of the linear momentum and the radial distance of the particle from the axis of rotation. Therefore, L equals rp equals mrvt, 11.15. The units of angular momentum are kilogram meters squared per second. There are no derived SI units for angular momentum. Recall that tangential speed is related to the radius of the circular path and the angular speed by the formula. Vt equals Rw. So, angular momentum for a single orbiting particle is L zur mr hat 2v, 11,16. Similar to linear momentum and external forces, angular momentum is conserved unless an external force is applied to the rotating system. For example, when a mass is whirled on a string of radius r with an angular speed of O, if the string's length is reduced to half the radius, its tangential speed must double, and its angular speed must increase as the square of the change in tangential speed. This is the same principle that a competition ice skater uses when performing a spin. His rotational speed is slower with his arms extended and much faster when the mass of his arms is held close to his body. Assuming that no external forces act on the system, delta L equals m squared r squared, square W2 minus m1 r1. Square W1 equals 0 kilograms meters square per second. M2 R2 squared W2 equals M1 R1 squared W1. Mass doesn't change, so M1 equals M2 equals M. The radius reduces to half, so R2 equals R1 over 2. Substituting MR2 squared W2 equals MR1 squared W1, W2 equals 4 W1. The angular speed of the mass quadruples. Angular momentum of a particle is a vector quantity, that is, technically, the product of two vectors, tangential momentum and the radial position vector. While its magnitude can be found from either equation 11.15 or negative 11.16. Its direction is found using the rotational right-hand rule, see Chapter 7, with the fingers of the right hand curled around the rotational axis in the direction of rotation, the extended thumb points in the direction of the angular momentum vector. Counterclockwise rotation has positive angular momentum.